In question 2.4, we've been given an identity and we need to prove the identity. So we're going to start off by grabbing the more complicated side of the equal sign. So the left hand side looks very complicated. So we're going to start off by grabbing the left hand side. And now I'm going to analyze the left hand side. Now the alarm bells are ringing. I see tans and I know an identity for tan. And these identities, you've got to know them off by heart. They are not given to you. So a tan theta is equivalent to a sine theta over a cos theta. So this tan of alpha, I can change it to sine alpha over cos alpha using that identity. So you can see the change happening over there. And then this tan of alpha, I want to do the exact same thing. I want to change it to a sine alpha over cos alpha. And once that change has been made, I'm going to focus on this fraction here. And ideally, you want to try to do this all in one step. So what I'm going to do is tip and times. Let me walk you through that process. So I rewrite it in the form 1 divided by sine alpha cos alpha. And then I'm going to tip the fraction, which means I swap the numerator and the denominator. And at the same time, I change this to a multiplication symbol. Just like that. And then 1 times anything is anything. Like 1 times 7 is 7. 1 times 2 is 2. So this 1 times can actually disappear. And now it's fully simplified. And now we're going to analyze what's inside the brackets. And I'm seeing a fraction plus a fraction. And when I see a fraction plus a fraction, that really triggers my brain to get an LCD. Now the LCD has to encompass both of the bottom's factors. So if they don't have anything in common like we have here, you just multiply them together. So the LCD in our case will be sine alpha cos alpha. Right, now we need to get both of those fractions over the LCD. So if I analyze this first fraction, I look at the denominator, it's got a cos alpha, and if I look at the LCD, it's got a cos alpha, but it needs a sine alpha, so that's what I need to multiply it by. And then just remember, whatever I do to the bottom, I have to do to the top. Okay, that sorts out the first one. Let's direct our attention to this one. It's got a sine alpha, but it needs a cos alpha. So over there, we need to multiply the bottom by cos of alpha. Okay, and now we're going to sort this mess out. So over here, I do the top times the top. Sine alpha times sine alpha will give me sine squared alpha. And if I multiply the bottoms together, we're going to get the LCD like we prepared for. So cos alpha times sine alpha gives us the LCD of cos alpha sine alpha. And now we're going to focus on this fraction. Cos alpha times cos alpha will give me cos squared alpha at the top here. And at the bottom, I've got sine alpha times cos alpha, which will give me my LCD like I planned earlier. And now that they're both over the same denominator, we kind of morph them into one big fraction like this. And now we've finished the process of getting the LCD. And now, yes, I can smell an identity, but it's cooking in the kitchen. So if you have a look at the top there, then from the list of the identities I know off by heart, that thing can just change to engine number 1. So we are going to go ahead and make that change. And now I can multiply the two fractions together. So to make my life easier, I'm going to put the sine squared alpha over 1. And then I say top times top. So sine squared alpha multiplied by 1 will just give me sine squared of alpha. And then I do the bottom times the bottom. So 1 times this, it won't change anything. That 1 kind of just disappears. And you're left with sine alpha cos of alpha. Now we can cancel here, because we've got 1 term over 1 term. So let's see what cancels. So over here, the sign at the bottom will cancel with one of the signs at the top. And I'll show you a better way of seeing that. So Sine squared of alpha is just a fancy way of writing sine alpha times sine alpha. So if we had to expand it into that, then these two sines of alpha would cancel, and I'm only left with sine alpha over cos alpha. And what I'm left with there is a trig identity. It's going to change into a tan of alpha, and we have arrived at the right hand side 17 years later. And your 5 marks come from using identities to change this tan alpha, using identities to change the 1 over tan alpha, and then changing this sine squared cos squared to a 1, adding the fractions together, that step where we did the LCD, as well as your conclusion. And just a small note on your conclusion here, you've got to say equals RHS. So we've got to prove the left hand side is equal to the right hand side to adequately prove an identity. And rounding out question 2, it says hence determine the general solution of this weird thing. Okay, now this is quite a big clue, hence. If you see the word hence, it means you use your previous answer to help you. So my eyeballs start looking up. I start going to the previous answer and I'm looking, how can that help me? So it looks quite similar. I've got a sine squared alpha there. I've got a sine squared alpha there. This bracket is slightly different. And also this side is slightly different. So I want to make this left-hand side look like the left-hand side of the identity so I can use it. And what I'm seeing is a tan squared alpha here. But over there I've only got a tan alpha. So to change it into a tan alpha, I need to divide both sides of the equation by tan alpha. And then on this side, the tan alphas cancel and we're just left with root 3. And when I divide this side by tan alpha, it's a little bit tricky. So you must only divide one of the factors by tan alpha. If you divide both of the factors by tan alpha, you're dividing by tan twice, so you're dividing by tan squared. So I only want to divide factor 2 by tan of alpha to get this identity. And if there's addition on top, I've got to split up the fraction and divide them by tan alpha individually. Just like that. So tan squared alpha over tan alpha will give me that tan alpha as I planned for. And 1 over tan alpha can't be simplified, so we just leave that guy there. And now you can see we've got the identity. It sounds basically the left hand side of the identity is matching up with the left hand side of our equation. So this whole thing over here is equivalent to tan of alpha. So I can change this whole thing over here to a tan of alpha. And as discussed, we just changed it to a tan of alpha, and now we are back in a familiar territory. So now I can go ahead and get my reference angle as well as my quadrants and general solution. Okay, so I'm going to start off by doing a small cast diagram, and over here I can see that tan is positive because it's just positive root 3. And in my cast diagram, tan is positive in those two quadrants, the A and the T quadrant. But the beautiful thing about tan is you only need one general solution. So I'm only going to do the first quadrant because it's a lot easier than the third quadrant. Once we know what quadrant we're working in, we're going to get the reference angle. And how I get the reference angle is I take that tan over and it becomes shift tan. And then I put in the root 3 there. So shift tan of root 3 will give me a reference angle of 60 degrees. And then I start off my general solution like this for quadrant 1. And then I always put an angle on the left over here. And then because I'm in quadrant 1, I just put the reference angle straight over there. And then next to that, I'm going to have to say plus K180. I use 180 for tans and 360 for sines and coses. And then next to that, I've just got to put a semicolon with K is an element of integers. This said with the 2 strokes is a short way of writing the word integers. And then we have reached our final answer. Now there are various methods to do general solutions. The method we did here is called the QRS method, which stands for quadrants, reference angle, and solution, just in case you're curious. Okay, let's have a look where the four marks are coming from. The first mark comes from dividing by tan of alpha. Second mark comes from using the identity to change the left hand side to a tan of alpha. Third mark comes from the general solution, and the fourth mark comes from k's and elements of integers.